Hello everyone. Today, I would like to make a short presentation of the dynamic framework that we have developed, which analyzes and visualizes knowledge exchange, programming questions, and development issues regarding medical applications and software. As we all know, the medical community is reliant on the ICT community, requiring software engineers, data scientists, data engineers, and other specialties to develop effective and practical solutions to be used in various tasks such as patient treatment, disease prevention, case tracking, and other things. The medical community is rapidly adjusting to the emerging developments in artificial intelligence, big data, and machine learning, and we expect its trajectory to be ever growing in the near future. In more recent times, the COVID-19 pandemic further highlighted the need for the programming community to offer efficient software, data pipelines, and solutions to tackle a global crisis. The responsiveness of programmers to face this challenge can be tracked and examined by studying popular question and answering portals such as Stack Overflow, where programmers can ask their queries on development issues, methodologies, and other problems, and exchange knowledge. Hence, by acknowledging the value of Q&A portals in profiling the technological interests of developers when producing software related to medical applications, we have developed a data-driven framework that accumulates data from Stack Overflow, filters them based on their relevance, stores and analyzes them based on several methodologies, and presents the results in an engaging platform. The framework has the ability to capture the interests of developers, showcase trendy technologies, and provide a picture of the questions and issues that the programming community has when developing medical applications. In this video, we present a case study of our framework on COVID-19 related questions, which has been the result of an extensive 3-year research where we profiled COVID-19 trends in Stack Overflow and extracted valuable insights. Of course, the user can use the framework for any medical topics by adjusting the search query, as we will see later. Let's start by showing the architecture of our framework, presented here. Overall, we designed the framework as 4 interconnected components, with each component feeding data to the next one. As we can see, we have the data collector that is responsible for collecting data, as the name implies, the predictive and storage component responsible for filtering and storing questions, the feature and knowledge extractor that does the heavier lifting in data mining, thematic analysis, and technology analysis, and finally, the visualizing medium, where all the processed information are visualized in an intuitive interface. Let's start by showing the data collector. The data collector's main function is to access Stack Overflow and retrieve question data. The collection is based on a user-defined query that can collect questions which contain specific terms. For example, in our COVID-19 case study, we had 5 keywords in our query: coronavirus, COVID, SARS-CoV, and other words relevant to the topic. If the user would like to explore another topic, such as issues in medical applications for cancer, for example, he or she could change the query to include cancer-related keywords. This provides the data collector with flexibility, as all the framework's pipelines can be replicated for any query and are dynamically adapted. Once the query has been defined, the collector accesses Stack Overflow and retrieves question data. Let's see an example of a question. As we can see, the question has several useful features, such as the title, the body, the tags, which reflect the technological objectives and can be from 1 to 5, the user that asked the question, along with a timestamp, and several metadata, such as votes, views, number of answers, comments, if they exist, and other things. The answer also carries a timestamp, allowing us to see how long it took for a question to be answered. Our collector retrieves several features, which are shown here, but these features will also be shown in the next component. Finally, the data collector has another useful function, which is updating the already collected data in the database. There are several features, mainly metadata, that change over time. For example, a question may receive more votes, answers, or even a first answer with a timestamp over time. Hence, the collector is responsible for updating the questions on several fields, provided that they have changes. Now we can showcase the storage component, which receives structured web documents from the collector, with the web documents being the questions with their features, and initially performs a filtering process. The filtering process is required, as no matter how specific a search query can be, there are always questions that will be irrelevant to the subject. For example, in our COVID-19 case study, there were questions that did have the word coronavirus in their text, but they simply mentioned it as an inconvenience that made the user work from home, or they wished other users safety from COVID and then proceeded to ask about a completely different subject. These questions had to be filtered out to keep only relevant questions. To do so, and to automate the process, we have constructed a machine learning classifier that can discern COVID-19 software development questions from irrelevant questions. We have used the sentence BERT transformers to create embeddings, along with the Adasin oversampling technique for imbalance handling. The training dataset was a readily available dataset from our previous research, and the XGBoost algorithm was used, along with the tenfold validation process. The classifier is used to predict the new questions gathered by the data collector every week, and has achieved an accuracy of 0.96, same with precision and recall, along with a 0.92 Cohen's kappa and Matthews correlation coefficient. In the future, we plan to expand the classifier and train it to more medical applications data to be able to predict question relevance on more topics. Having filtered the questions, the storage component proceeds in saving them to our database as records. For our database, we have selected MongoDB, as it is an excellent CRUD database that handles textual information well. Let's see a record example in the database. Let me just find a good question. So, as we can see, the example is a retrieved question where all the features that we retrieve are different fields. Each question carries a unique ID by the database and an ID of its own here, while we also keep the name of the user that posted it and textual information such as the body and title. In addition, we keep the timestamp of the question along with the timestamp of its first answer, provided that it exists. We also keep several metadata such as the votes, views, the location of the user that posted the question, and the coordinates of the location, which are taken from the next component, and also several useful information such as the number of comments, answers, whether the question has a code snippet, which most of them do, while we also keep whether the question has been closed or deleted, indicating low quality or duplicate questions. This allows the user to choose whether he or she wants the deleted or closed questions to be included in the analysis. Finally, we keep the tag feature, as tags indicate the technological aspects of the question. For example, here we see that this question is relevant to the R programming language and some data handling processes. A final feature that we keep is tag combinations. As the tags co-occur together in questions, we can say that there are pairs of tags. This is a very important indicator of tag popularity. Hence, we keep all possible tag pair combinations in this field. Let's move on now to the feature and knowledge extractor, the most important component of our framework. Here is where all the feature engineering and scientific analysis procedures take place. A first operation is the deduplication of questions based on their ID. In addition, the provided user locations are geocoded into coordinates, while the textual information, the title and body, are subjected to natural language processing such as stemming, tokenization, stopwatch removal, and some other operations. Finally, given that the question has a first answer, we compute the elapsed time in minutes that the question took to be answered. As far as the tags are concerned, we first of all merge similar tags to each other. For example, the tags Python 3.5 and Python 3.1 both refer to different versions of the same language, and they are both simplified to Python. We have an automated process that merges as many tags as we could find to simplify the tag analysis procedure. In addition, many of the main tags are distributed in technological domains based on a pre-constructed lexicon that we have used in our previous research. This lexicon has 7 categories that are relevant to different ICT tools, such as web frameworks, languages, databases, platforms, and other categories. The lexicon can be shown here, with some main tags belonging to the respective category. We should point out that while here we only see the languages, some tags may belong to more than one categories. This lexicon was constructed using the Stack Overflow developer surveys, where the main technologies used by developers are highlighted. Once the feature engineering process is complete, we pass to the knowledge extraction phase. Here we have three main pillars of analysis, apart from the extraction of useful descriptive statistics on metadata. The topic analysis involves the use of two algorithms in the textual features, the body and title, to extract thematic circles and topics. We make use of the latent Dirichlet allocation algorithm, or LDA, a staple in topic modeling that produces a probability distribution of topics in documents, with documents being Stack Overflow questions in our case. The number of topics is determined by the coherence metric, which calculates essentially how well does our LDA model explain the documents. Each document belongs to each topic with an assigned probability, called the membership value. And higher values indicate more dominant topics. The second algorithm is the BERT topic technique, which uses embeddings of non-processed text to project them in a two-dimensional space with the UMAP methodology and assigns a single topic to each document. Then, by using the HDBScan clustering algorithm, it creates document clusters that belong to the same topic. We use the preprocessed text in the LDA algorithm, while for the BERT topic we use the raw text. As far as the elapsed time between the question posting and the first answer is concerned, instead of simply examining the elapsed time distribution, we wanted to see the level of difficulty, in the sense that a longer elapsed time for an answer means a more difficult question. Hence, we use survival analysis, a methodology that originates from epidemiology and examines whether a terminal event, in our case the answering of a question, may or may not occur in a specific time frame, in our case the elapsed time. In this method, we have censored data, or questions that did not receive an answer in the entire period of collection, and uncensored data, which are answered questions in a given time frame. The survival analysis estimates the probability of a question being answered at a certain point in time, and visualizes this information in a probability curve, where the x-axis is the elapsed time, and the y-axis is the probability of answering in this elapsed time. A steep curve indicates shorter times and easy questions, while a flat curve indicates longer times and more difficult or even unanswered questions. Finally, in the tags analysis, apart from presenting the most frequent tags in all the questions and per technology domain of our lexicon, we also focus on tag pairs. At the first level, we simply present number of times that highly frequent tags that appear many times in questions occur together. However, our goal was also to delve deeper and see tag pairs that are truly linked and always appear together, despite not necessarily having the highest frequency. This is really useful as it reveals more interconnected and dependent technologies that may go unseen in a simple frequency analysis. To do so, we use the inclusion index, a cohort analysis metric that for a tag I and a tag J is computed by dividing the frequency of the tag pair occurring together with the minimum single frequency of the two tags. It is essentially a conditional probability that can be interpreted as the probability of a tag appearing in a question given that another tag is in the question. The inclusion index ranges from 0 to 1, with a value of 1 indicating pairs that always appear together. We should point out that one tag may appear in other questions as well, but it will always appear in questions that are labeled with the other tag. Having explained the architecture of the previous components, we can finally see the visualizing medium. This component is the one that the user sees, where all the visualizations and the methodologies of the previous components are put together in an easy-to-use interface with an easy UI and UX that shows the insights of our research. The medium presents the insights from the temporal, semantic, and technology analysis, and offers functionalities for the observation of trends in the given topic of medical applications. Having seen the architecture, we can proceed in showcasing the results of the visualizing medium, tailored to our COVID-19 case study and named COVID Flow. This is of course just a placeholder, as we plan to expand the interface and deploy it publicly. Let me open the interface. Okay, so we go here. Alright, so this is the main screen. At the first glance, we have the overview, presenting some useful information about the interface and our related research. So here we have a description of the interface and some references for the user to be able to see the additional research. The metadata panel shows some useful insights about the number of questions, the users, and other metadata. For example, we can see that in a given time frame we have 2,000 questions from a distinct number of users, indicating a developer interest. However, this is a time slice of the entire period, so I will adjust the time frame now. So, from this window, the user can adjust the time frame. I have now selected the whole data collection period of 3 years, but these are fully adaptable and dynamic to any date range. In addition, this box here allows the user to include closed and deleted questions or not to the analysis. Note that this panel is quite dynamic and the user can select any date range that he wants. For example, here I have the whole collection period, where we see that we have almost 5,000 questions from a high number of distinct users, and these average metadata show user engagement. Let's move down and see the line chart of COVID-19 related searches. Here we see that the peak of question posting was around March and April, where the first lockdown was announced, with successive peaks corresponding to additional lockdowns, vaccinations, or surges of the COVID-19 in different periods. Moving further down, we can see the distribution of several metadata such as votes, comments, answers, and views. As we can see, many questions don't receive votes, and some of them do receive a number of votes, but some of them also receive negative votes, indicating low quality questions. As far as the comments are concerned, they seem to follow a power law distribution, where many questions have 0 comments and some of them have a large number of comments. The same goes for answers, with much of the questions receiving 1 answer and many of them receiving a different number of answers. Finally, as far as the views are concerned, we can see that we have most questions in the range of 4 to 100 views, but there are some outliers with a large number of views. Moving further down, we can see that we have the word cloud of the most used tags in questions, where we can see that we have technologies with programming languages such as Python and JavaScript, some machine learning tags such as machine learning, deep learning, and for loops, and some web frameworks such as React.js, Vue.js, Node.js, and some forecasting related tags such as time series. Of course, we can see that we also have some database technologies such as MySQL. This indicates that many of the tags are relevant to data manipulation, web design, and machine learning. The top 10 technologies validate this finding, with tags such as Python, R being dominant languages for data handling. We also have some web design languages such as JavaScript and HTML, dedicated libraries such as Pandas and web scraping, and some frameworks such as React.js. So, moving further down, here we have a world map where we can see the locations of users that posted SO, Stack Overflow questions in general, but in our case, COVID-19 related questions. Here we have a point map, but the user can also adjust the map to be a heat map, where we can see that the red regions have a higher presence of Stack Overflow posted questions. We can see that most of the regions were particularly hit by COVID-19, such as the USA, Latin America, India, and Europe. If we zoom in on the map, we can see a more refined distribution of the locations, where we can see which regions truly post SO questions related to COVID-19. Moving further down, we can see a radar chart depicting the technology domains and which domains are mostly used in question tags. This means that the tags that label the questions belong to technology domains, and we can see which domains are more present in questions. The radar chart indicates that the languages technology domain is the more dominant, with most of the tags in the questions belonging to this domain, which is an expected finding. Also, we can see that the platforms and developer tools, along with web frameworks, have an increased presence, which is also an expected finding based on developer interests. In addition, here we have a chart of the questions that contain code snippets, which most of them do, an expected finding, and of course, a chart of questions that contain answers, with almost 25% of them not containing an answer. Here, this table is one of the most the most influential content of our framework, which is a table that sorts the top 10 questions both by technology domain and by selecting all the questions if the user wishes to do so, and also by several metadata. For example, let me check all the questions that belong to the languages technology domain. We should point out that this distinction is made by the tags that have been labeled in the question. As we can see, I can sort the questions that belong to the languages domain by several metadata such as votes, answers, comments, views, and also by the minimum and maximum response time. If we click here, we can see, for example, that this question took almost a minute to be answered, which was quite fast. And if we click here, we can see that indeed this question was answered in almost a minute. Oh, here, this is the first answer. And this is indeed a minute after the question was posted. And we have another answer here, which is a little further well. If we click on another question, we can see that indeed this question was answered in just a minute, which is a pretty fast response time. We can also sort questions by their maximum response times. Of course, this question is deleted, as I have included deleted questions in my query. If I did not have, the first question would not be deleted. For example, we can click here and see a question that isn't deleted, but took a long time to be answered, almost 2 years after the posting of the question. In addition, here we have the top 10 users that post COVID-19 related questions, though this can be adjusted for any medical topic, as we have already mentioned. Moving further down, we can see the results of the topic analysis, where we have used the BERT topical methodology and the LDA methodology to extract topics from the titles and bodies of the question. Here are the results of the BERT topic, where we have extracted 29 topics, with each question being assigned only one topic. We can see that most of the topics are related to data plotting, web scraping, web frameworks, machine learning, and other stuff, such as technical topics which have problem solving, word string sentence, list, dictionary, deployment with Heroku, frameworks such as Flutter, Shiny, React, visualizations with Seaborn, Tableau, ggAnimate, which all reveal very interesting research pathways. Of course, this plot was produced by Plotly and is fully interactive. If we click on only one topic, we can isolate the questions that belong to this topic and see them as a separate community. And if we zoom further in, we can see the questions that belong to this cluster and see their titles for a more detailed insight. Let's click here to show all the topics. In addition, here we see the hierarchical concept of BERT topic, with the main topics being subdivided in smaller topics. Also here is a result of the LDA analysis, where we have a model that explains the question titles and bodies with 9 topics. Here, a larger circle indicates a dominant topic, which is more present in questions. We should also point out that the topics are projected in a 2-dimensional space using the multidimensional scaling technique. The distance between topics indicates how similar or dissimilar they are. For example, topics 1, 2, and 3 are more similar to each other than, for example, topic 1, topic 6, or topic 5. The smaller the circle, the less this topic is present in questions, which may reveal more technical or more difficult topics. If we hover on one topic, we can see the keywords that characterize it. For example, topic 1 is relevant with data handling with Python, R, and some other interesting terms such as date, pandas, data frame, error, map, which reveal the interests of developers. By hovering on other topics, the user can also see different research pathways and developer interests. If we go further down, we have the results of the tag analysis. As a first glance, we provide the chord plot, which reveals the most frequent tags and how many times they co-occur together in questions. The user can select all the groups or go to a specific technology domain and see the tags there. Let's say in all groups for now. For example, we can see that the leading tags are Python, R, JavaScript, pandas, and HTML and web scraping, an interesting finding. If we hover on Python, we can see its connections with several tags such as pandas, JavaScript, web scraping, HTML, JSON, Beautiful Soup, and others. In addition, by hovering on any line, we can see additional information about the number of times that these two tags co-occur together in questions. In this table, we also see the top 10 co-occurring tags based on the inclusion index. As we said previously, these are not necessarily frequent tags, but they are tags that always co-occur together in questions, having an inclusion index value of 1. Here we can see technologies linked with the GitHub API, GitHub Pages, Python and the Euro PMC technology, and some Python and data cleaning procedures. We should point out that the inclusion index was not conducted only for tags belonging to the technology domains, but for all tags. Finally, let's move on to the results of the survival analysis, where at the first glance we see the median time elapsed until the first answer per technology domain, and for all questions. As we can see here, the platforms and collaboration tools have higher response times, indicating more difficult questions that require experienced users to answer them. Here are the results of the survival analysis, where we have the Kaplan-Meier curves. As I said, a steep curve, which ends abruptly, indicates that the questions of this category are being answered in shorter times than other curves. For example, the database curve indicates that all database questions are being answered in a relatively short time, while other curves, such as web frameworks, languages, big data, and all competence groups, take longer to be answered and may not even be answered at all. This finding may be interpreted in a way that the database technology domain attracts more experienced users that have the capacity to answer questions in a shorter time, while the generic technology domains such as languages and web frameworks attract many users that may not have the insight to answer questions and provide wrong answers, thus elongating the response time of questions. Finally, down here, we have the question distribution for all groups and per technology domain. The user can select to see the distribution of open, deleted, and closed questions in each competence group. For example, the web frameworks group has 3 closed questions, 70 deleted questions, and 809 open questions. Of course, the user can see the collective distribution by just selecting the all groups option. As I mentioned previously, the framework is completely dynamic and the user can select to adjust the timeframes. For example, let me select the whole of 2020. Let's put it here, and I will select not to include the closed and deleted questions for a more collective view. If I press search here, we can see that the framework is being adjusted to the new data, with the metadata panel being changed, and of course the metadata being changed as well. The line chart has been adapted to the new data, showcasing questions until the end of 2020, while the question distributions, answer distributions, and views distributions have also been changed. Also, the most used tags have also been adapted. The user can pause this video to compare the two word clouds and see which tags were eliminated and if new tags emerged. However, we can see that the top 10 technologies have not changed and Python and R remain in the first spots. As we can see here, these charts are also being adapted with the percentage of answered questions being reduced. And of course, by sorting the questions, we can see that the metadata have been changed and the questions can be sorted by different criteria. The same goes for the top 10 users. Moving further down, we can see that the core plots have also been changed, while the top 10 co-occurring tags based on the inclusion index have also been affected, with R and D clear occupying the top spot. And of course, the median times have been adjusted to the change of the time frame. The same goes for the Kaplan-Meier curves, where for example the pink curve, the collaboration tools, shows that these questions are being answered in a shorter time frame than any of the curves, with all the categories being affected, particularly the big data ML category and the databases category. Finally, the question distributions have also been affected, with the numbers being reduced. As we can see, The framework is fully adjustable to dynamic timeframes and can show trends and developer interests based on the user's preferences. In the future, we hope to deploy the framework publicly, incorporate more applications, more scientific methodologies, and of course, improve the classifier to be able to predict different questions on different medical topics. Thank you for your attention, and I hope that you find this framework an insightful venture.